So welcome everyone. So homework 5, last homework. Um ah, Crazy. So part A, we'll be talking about showing the algebraic amplitude ratio, phase lag in series. That means like both of them are connecting in one other series, like kind of like the electrical system as well as when you can compare it to. We'll find the sum of the amplitude ratios and phase lags of the individual transfer functions GP, GC, GM in this case. And then we'll also show algebraically that the phase lag of a first order system asymptotically approaches minus 90 degrees. And when you see that asymptote, most of the time it's always going to involve the tan of like an angle in that case. And we'll show how it approaches minus 90. So also algebraically show algebraically that the two first order systems in series will always yield an overdamped. But we have overdamped the middle, like overdamped, properly damped, then underdamped as well. So I think when it's overdamped is greater than one. When it's like the regular is just equals to one, then when it's underdamped it's less than one. So we'll have to show why it's going to be greater than one. Then we'll derive algebraically the phase lag for a pure time delay transfer function. Then lastly, for part A, we'll show and explain how a first order system with time delay may become more stable with proportional only control. So yeah, we'll just be adding a few. It's basically we're going to use what we did for homework 4. We're going to add a few things to show how the instability comes in over time as we're working on it. So for the first part, we'll be working with the like deriving the functions that we're going to use throughout this process really. So let's get into it. So yeah, okay, this is good. Perfect. Oh, oh, two there. I think this is okay. Sure. Okay, I feel like this is. I'm just reduce it a bit. 14. And I feel like we'll be ready to go. This is too much as well. Okay. I feel like that's the perfect. So now let's get into the derivation. So like I said, when they're talking about in series, it's basically like I said, so similar to what we use when we're like talking about resistors in series. So you see it like connected in this way and it's flowing through like a system. So kind of like that. So it's kind of like this. So it's kind of like this in this case, and that basically goes the whole way, really. So we'll call this our first transfer function, and this will be second one in this case. So now, when it comes to like the transfer function, so from what we're used to, always involves like the real image and like the RI. In this case, so when I series is basically G1 times G2. That's going to be equals to the R plus I. This is basically what we talked about. J multiplied by the for G2. It's basically G2, G1 represents this, G2 will represent what we're about to write as well. R2, and I want to write G again. I2J. So this is basically how it works. Then when I show, we'll basically open it up from here, really. So we're opening up the bracket in this case, so that will be R1 times R2. Then we have R1 multiplied by I2J. Then we have R2 plus R2J. Yeah, R2 plus I1J. Then we have I times I1 times IJ, basically. Plus, sorry, there's a plus here. So it's just the I multiplied by the I. So yeah, I multiplied by J multiplied by J. J is basically -1. So -1, square root of -1 times square root of -1. So we'll just do minus I1 times I2. So we're good on that part. So now it's just basically to group these terms. So we can group it like this. We can be like R1, R2. So J is the common factor here. So we'll put J out. And we'll have R1, I2 plus R2, I1 minus I1, I2. So now we're good on that case. So now we can go ahead and basically find what our amplitude ratio is in this case. So from this, we already know when we're grouping stuff like this, we have the J was with the J and we have what's separated from like the normal variables. So when we put that together, that's going to be R1, R2 minus I1, I2. Then we have the J bar, R1, I2 plus R2I. J. So this basically represents what we're looking for in this case. Let me just keep going. Because I know you complain about like the visibility. I feel like this is good. So just keep on scrolling up and down from here. So now basically this will give us what our values will be. So we have this portion and we have this portion. So that's basically going to be what our values will be. So our amplitude ratio, we'll say, is the square root of the square of these two. Squared plus R1, I2, 2, I1 squared. Again, we'll open up the brackets. So when we open up the brackets to give us, this is meant to be long. Yeah, this is just, I was gonna say it's just the difference of two squares, but it gets me much more. Okay. Okay. I'll just quickly work that off. Right. Yeah. So that's basically going to be R1 squared. Yeah, R1 squared, R2 squared. Then we'll do minus 2I from what I got. Minus 2I1, I2. Then we have R, we'll account for the R1s as well, plus I1 squared minus I2 squared, then plus I1 squared R2 squared plus 2I1, I2, R1, R2 plus R1 squared, I2 squared. So from this rule, whenever there are things like this, there will always be like cancellations because there will always be common terms. So these two will be able to cancel out. So we're now left with like these. And you see something common is like there's always these terms that have um like the common things like the R, the I. So when we look at this, we see okay, this is just going to be difference. It's kind of like going to be the difference of two squares as well in this case. So we'll say AR, the amplitude ratio. Amplitude ratio is going to be okay. So we have this R. Let me bring it together first. R1 squared, R2 squared, plus I1 squared minus I2 squared, plus I1 squared, R2 squared, plus R1 squared, I2 squared. Okay, this just seems like okay, so it's R1. So definitely we'll have R1 and R2 on one side. That's clear. And we also have the eyes. Yeah. So we're going to do something like this. So it's going to be R1, R plus. So R1 plus I1 squared plus R2 squared, then plus I2. Yes, it's good. Yeah, this is good. I2 squared. Sorry, there must be a minus. Sign to be a minus. Oh no, there's not even meant to be a sign. Because this is just like a combination. Okay, let me see. That's good. Or okay. Yeah, so it's going to be a square here as well because the R1 squared must be over the R2 squared. I don't think this is not meant to be minus. Yeah, okay. Yeah, I feel like we're good. So yeah, this is it really. That was not meant to be a that was not meant to be a subtraction in that case. That was meant to be like multiplication. So now basically we have our amplitude ratio. So now it's just to find what the phase lag value will be. So it's really just to find, okay, what is it going to be in terms of what's going to be the X and Y value. So when you're finding like the tan inverse or something is going to be tan, like the Y over the X. That's basically what we're going to do in this case. So in this case, we'll put like tan is going to be, so we'll put like I1 R2 plus R1 I2. Then we'll do R1, the two R's minus the two I's. So now we know, so when it comes to, since they're like two different variables, you're looking for the R1 and R, like the RI, basically the two, there's going to be the one and two. So we'll account for one, this will be R, there's going to be the 1 over R1, which means it's going to be close to I2 over R2. So, and when it comes to this plus this, that's what makes this. So the inverse of this plus the inverse of this, that's what gives us this whole, the tan inverse of this is what gives us that, basically. So that total is equals to this plus this. So that's the whole math, and that's the whole gist about this situation, really. So that's where we derive this phase lag from, and what leads us to what we'll continue to calculate over the line. Okay? But yeah, we're not done in this case. So now we know we're going to involve two phase lags, basically. So now we're going to account for both of them in this case, and that's what we have to do. So now we have to, so we know we're adding them. So when we're adding it, that's what going to give us basically our phase lag in this case. So, I'll just scroll up here. I'll scroll back up. So about this. So yeah, as we know, tan, let me just use this. This is going to be the same as sine over cosine. So that's basically what we're going to do in this case, because now we're going to consider this plus 2, which is equals to basically like the same ideology over cosine. So that's basically the ideology that we're going to use in this case. So now we're going to open up the bracket as well, because we want to expand this in this case. So when we open up this bracket, so basically give us this. So it's give us something similar to how we mixed it up here. Because we know what I will be, we know what R will be in this case. So sine that, multiply by cosine this. It's basically like this, like I was saying, we just flip. So it just shows like the I is going to be R1 is equals to sine this, and R2 is equals to cosine of this, really. So now we have sine 2 cosine 1. It's that direct. Then similar to what they did, there's the below one was the R2 minus. So yeah, we know what R is cosine, we know what I is, we know that. So that's basically cosine 1, 2. That was a negative sign up there. Yeah, when we do like the algebraic part of things, we know this is going to give us, put that equals to there. This is going to give us basically this So this is going to give us the tangent plus tangent of this over 1 minus the tangent. But basically, I think what we're going to do, we're dividing all through by the cosine. That's why. So yeah, that's why it's going to look like this. So we're dividing all through by cosine. So you know sine over cosine is equals to tan. So yeah, so it goes across really. That would be tan 1 done 2. So I hope that was quite clear really. We just took out, we just multiplied all through by a specific thing for us to be able to get what our like variables would be. Yeah. So yeah, I feel like from this now we can easily see what I is. We can see what each one represents. So we can be like, okay, so this I1 R2 is going to be a tan 1. Then we know this is going to be tan 2. Then we know R1 R2 is equals to 1. And we know I1 times I2 is equals to tangent 1 times tangent 2. So now we know, basically, we can basically see that they're all connected at the end of the day. And basically, that's what it stands for, really. So we could also say this tangent is going to be the fact that we divided it by cosine, because we know the R was the cosine, and yeah, the R was the cosine and the I was the sine, really. So that's we could also say I over R. This is going to be I over R. It's going to be I over R2. This is 1 minus I over. That's basically like the gist of the whole thing, basically. So let me just write that. So I2 over R2 divided by 1 minus R1 multiplied by I2 over R2. So now basically we have what our equation is going to look like. We know what our amplitude ratio is going to look like, and we know what our phase lag is going to comprise of, basically the sum of the first phase and the second phase as well. Second order, first or second order, really. So that will give us what our phase would be. So let me label that. Let me say this is A. So now let's go to part B. So part B says, show algebraically that the phase lag of the first order system asymptotically approaches minus 90 degrees. So we're going to have to use basically the formula that we used earlier for those to get like for those 3 tanks, like that height. So you know how it was that K meant something. Then we also had B, I mean we also had tau, that tau meant something. S K equal K over tau X plus 1. That's basically what we used. So now we're going to replace, you know how the S key S is equals to JW. So we're going to incorporate that again. We're basically going to solve in this instance, really. So now, like I said, K, as we said, is when I put K close. So we know the transfer function was K over tau S plus 1. And like I said, S is equals to JW, which is K 1 over tau JW plus 1. Then now let's see. So yeah, trying to bring this down. So yeah, this is also going to be equals to K, which we got earlier. Then 1 minus tau S, oh wait, JW really, divided by 1 plus tau. Because if you know when is the square of J, that's just basically going to be minus 1. So the reason why it's like this is because we squared, but basically multiplying the denominator and denominator by this 1 minus this. So when you can see each of them have their own squared, so each of them multiplied by each other, how we know J is equals to -1. And when you have -1 squared, the square root of that's going to be -1. -1 will multiply all through, and it should just be positive at the end of the day. So yeah, this is another way. It's just another way of writing it really, so that we'll simplify and find like the square roots at the end of the day as we're finding what the amplitude ratio is as well as the phase lag will be. Okay. So now we can move forward with this. Let me go back to the page. No, it's not showing. But yeah, so now we can find the amplitude ratio as we said. Amplitude ratio is going to be K. So the amplitude ratio is going to be K multiplied by the square root of 1 plus W squared. What happened J squared? Keep on forgetting the tau. This is going to be tau squared divided by the same thing. 1 plus W squared, then tau squared. So you now see how it all flows together reading. So now we want to be able to find what our system will be in this case, and that will be, so it's just basically this divided by that. And this is just going to be, basically the same thing, but this one is to the power of half, this one's power 1, half minus 1. So that's basically going to be equals to K multiplied by 1 plus theta -1/2. So basically K multiplied by 1 over 1 plus W tau squared with this. So that's just another way of writing it, basically just the inverse of the squares in that case. So now when we're finding the phase lag, we're always going to do like the sine over the cosine in this case. So basically what we had before, we're basically going to manipulate that in this case. So I don't know why I keep doing this. So let me not stop on 11. So the tangent of the phase lag, basically was this. So let's get this, yeah. So it was this. Okay. Divided by. And now we'll divide it by 1/1, then tau squared. So basically, for sure, this will cancel out. Yeah, this bottom, the denominators will cancel. I mean, the denominators will cancel out. This one is going to go either way. So that's not meant to be one. So now we're going to do just going these two are going to so it's just going to be tan base equals to minus tau w. I don't know why this j is there. The j is not meant to be there. The j goes because it's going to be squared, so that's going to be negative. That's going to be -1. So -1 goes, so it stays so it's going to be this. So that means it's going to be minus tan inverse of this. And most of the time, whenever you're finding like the so I'm trying to look. I'm not really finding it, but this is mostly based on quadrants. So one thing that my high school teacher told me was all science teachers are crazy. So in this quadrant, all of them are positive. In this quadrant, only sine is positive. This quadrant, tan is going to be positive. This quadrant, cosine is going to be the main thing. So we know this is going to be negative. This is going to be positive side of x. This is going to be the negative side of x, y. I mean, negative side of x, positive side of x, positive side of y, negative side of y. So in this case, you know how it's going to be um this one that's saying the negative tan inverse of that. So now we know that. Let's see. So with the range that it's in, it's going to have mainly within 0 to minus 0 to initially the range is going to be 0 to 90, but with the negative here, it's going to be within that 0. It's going to be within that negative 90 to 0 range. It's only because of these quadrants. That's how it works. So whichever quadrant each of it fits into, then it's go according to that. So this is just like it's like a circle. Basically half is 3, 4, 360. Okay. It goes from there. So now basically we understand how asymptotically it goes to the negative 90 in that case. Okay. So now we'll go to part C. So part C talks about show algebraically the two first order systems will always yield overdamped. So let's first check overdamped. Yeah, overdamped, critically damped, underdamped. Okay, let me just quickly share this screen. So here we can see the critically damped is right on that line. It's right on that line. So it's basically like one. We'll say it's one. Then we'll see the underdamped is basically below. That'll be less than one. Then we have the overdamped, which is greater than one. So yeah, I don't know if this is the best. I'm trying to diagram. So here we can see the overdamp right above the line. Then we have the green, which is critically damped, which is on that line. Then we have the underdamp, which is below that line. So I feel like this is the best picture. Let me see this one as well. So basically, you get the gist of how each one falls under which one we. So now we'll just show because the question was about yeah, the question shows the first orders will always yield an overdamped second order system. So we're going to show why it's going to be greater than one in this case. Okay, so let me go to part C. So now let me go back to so now we're going to go to 3. We're going to show why it's overdamped. And about overdamped is when it's going to be greater than 0. So that was my fault. Greater than 0. So that's what we're going to be focusing on. Let me stop sharing. Okay, so now we can go into the aspect of why it's going to be, how it's going to be over 0 to show why it's always going to be basically overdamped in this case. So we're going to start from the transfer function. Let me go to part C. Let me just put 3. So let me just show you where I've been. So any confusions. Try to make it like a straight line this time. So now I want to show why over, down, greater than zero. We want to show how that. So most of it starts from the transfer function itself. As we're used to from before, we know like the transfer function was always like k over the tau squared multiplied by s squared plus 2 zeta tau s plus 1. So this was what 1 represented in this case. This was what 1, like the transfer function of 1 represented. And this is what like we used over time for the transfer function, for example. So now this is like the overall thing. So now we're comparing. It says show the first 2 orders. So that's K. We're going to look at K1 and K2. We're going to look for the 2 of each one in this case. So that's what we're going to work on. So we're going to show how they're related and how it gets us to where basically what we're looking for in this case. So now we have so we know K1 over tau s plus 1 multiplied by K2 over tau s plus 1 tau. Yeah, tau. Oh yeah, they have different taus. So it's just to show the discrepancies. So now let's multiply this K1 times K2 over tau 1s plus 1 multiplied by tau 2s plus 1. So now we'll just open up the brackets, K1, K2 over, so be tau 1 plus tau 2 no, there's no plus. This is going to be direct. Tau 1 tau 2 s squared. And these two will multiply, so that would be, so this is where it's coming. So 2s plus 1. So we're good on that. So basically this is going to be, we know this is going to be, this is the general thing, so equate that to it. So it's going to be 2 zeta s plus 1. So now one thing I love about this transfer function is that they always like show for themselves in this case because it just shows the relations. So this is equals to this. This is going to be equals these two. This is going to be equals these two. One of them is going to be 1. So now we have 3 functions that we're going to focus on. K is equals to K1, K2. Then in this case, the tau squared is equals to T1 times tau 1 times tau 2. Then 2 zeta tau is equals to tau 1 plus tau 2. So those are basically like the 3 functions that we have in this case. So we can basically work with that from here. So right now we know. So now we know another way of writing this is just, we'll just make tau the subject. So that tau is equals to tau 1, tau 2. So basically this is just another way of writing it, basically just to make what I put. Just another way of putting like tau on its own, just removing the square, just finding the square root of the other side in the reading. That's what we're going to do. And now, another thing I love is, so we know this is equals to, when you bring this to this side, it's basically over tau. And one thing is that we got tau here from this previous equation. So that's going to be tau 1 plus tau 2 divided by square root of tau 1 multiplied by tau 2. So that's the beauty of this. So now we have the square root, so we want to basically erase this square root. So now we find the square of both sides. So that'll be 4 zeta squared equals to T1 plus T2 squared divided by square root tau 1 tau 2. Oh no, I remove the squared. Tau 1 tau 2. Yeah, so now we can basically solve for each part. 4 zeta squared tau 1 tau 2 is equals to T1 plus T2 squared. So now, in the cases where the zeta is approaching 0, so that be 0 equals to. So let me try and explain that. So that's basically 0 equals to tau square 1. Yeah. Then Ti, that'll be 2 Ti, 2 tau 1 tau 2, then tau 2 squared. So basically now we have that sorted out. Let me try and analyze that properly. Let me reanalyze that. Yeah, we'll just do the squared is equals to how much did I delete? Is equals to T1 plus T2 squared divided by 4 T1 T2. Oh. So now, basically, we have the format that we'll go forward with. So let me just open up this one first. So recording. Yeah. So basically, now we basically have this formula that we're going to use. So this is always going to be greater than one. Like that's the standard. So now we'll just do we'll treat it like when it comes to inequalities, we always treat it like the equations really. So t1 squared plus 2 t1 0 2 plus t2 is going to be, this will come to this side. So this will be 4 t1 t2. So now, so yeah, this is always going to be greater than this. So that means is going to be towards that zero mark. Let's see what 2 plus c2 is going to be greater than, it's going towards that zero. It's approaching zero really. So we'll just go back to the original form. So this just shows that this just shows what it's going to look like as we're approaching that zero mark really, because yeah. So like the inequality, we know is always going to be greater than one. First multiply, make that equals to that. Then yeah, just solving for each one just shows like as it's approaching zero, is always going to be greater than that. So that means the general thing is like t1 plus t2 squared is going to be greater than zero. So that means that just shows how in comparison with the second order and the first order, how is always going to be yielding an overdamped second order system in this case. So yeah, most of it also comes from the amplitude ratio, because the reason why we'll see later on why like the as it approaches, you see later on why it approaches like the zero mark, mainly because of it mainly comes from the amplitude ratio. So we know the usual. So we know how we'll just start from where we all start from. The k, the transfer function is k over this multiplied by this. I mean k over this plus this really. Now, like we said before, that S is the same thing as JW. So we're going to put JW into wherever S is. So that was K. So this one. So this one is T tau squared. JW, that's going to be -1. So that would be minus this squared. Then we have on this side, we have the 2 T S D W plus 1. So either if it's to work, you can bring the 1 here. You can leave it the way it is. So for me, we keep on working because of like the what's it called? Because of how this denominator is built, for you to be able to cancel out values and factors, we'll basically multiply the numerator and the numerator and the denominator by the inverse of each other, really. So as we know, this is going to be k multiplied by, so that's 1 minus tau squared w squared minus 2 zeta tau jw. So now we're going to find like we'll do 1 minus tau squared plus 2 zeta tau jw. So this will be multiplied by 1 minus tau squared w squared minus 2 zeta. I'm just reading this. JW. So it always comes down to like the difference of two squares. Some will cancel out, some will remain. So now, yeah. So now we can just solve it from there. This will be equals to k 1 minus tau squared w squared minus 2 . So with it being difference of two squares, this would be this minus squared. Then this would be 4 times square of all that. So it would be plus 4 because, like I said, the negative, when j times j multiplies, it's always equal to -1. -1 times that plus 4. So 4 times zeta squared, tau squared, and this w squared. So that's what we get as our values. So now basically we have what our transfer function is going to be. Now this will lead us to finding what our amplitude ratio will be. This amplitude ratio will then give us like, we can go as far as doing So square root of divided by. So this is basically our transfer function is going to look like this. And as we know, this is basically just going to be basically the same function. So it will be it's just like an easy way to eliminate the 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 square roots. So from there. So that's basically equals to like 1/2. So right now we're meant to find the for when you're solving this kind of thing, for it to go to zero, we always find like the derivative. So we're doing it in terms of W. So we're doing it in terms of W. So now keeping in mind like this is basically to the power of half. So that'll be that half will come down plus negative half, since it's like below negative half come down, then to go to negative yeah, to go to negative 3/2. So it's just be 3/2 on the bottom. Yeah, they will just keep like what's up there. So let me work that, come back. So that's going to u minus k/2. Then we have that's going to be 2. Let me just look at my notes. Yeah. So that's going to be 2. That's 2t². Then this is in terms of so this is in terms of W, so 1 minus the, so basically this will remain the same, chain rule plus 8 times this squared on W divided by 1 minus T. To the power of 3/2. When we solve for everything, it's going to give us like, when you basically factorize for, so we have that TW seems like a common factor. 1 minus, yeah, 1 minus T squared W squared. So now this is going to be the this is like the derivative of the transfer function. And z when we put zeta equals to 0, it's to give us like what the max AR would be in that case. And yeah, so let's try. This is going to be 0. So this would lead us to getting like what maximum ARB. And that's with W being 1 over tau at the same time. So yeah, we've gotten how we've shown how it's like going to be that kind of like maximum value greater than 0 for the whatever. So it's 12 26 time. So yeah, it basically helps us get that value at the same time. Shows us why it's going to be overly damped greater than 0 in this case. So number 4 says derive algebraically the phase lag for a pure time delay transfer function. Okay. So I feel like for this part, it's basically the knowledge that we've used. So as we know, the tan is always going to be I over R. So this is basically sine over cosine. So that just shows that part. So now we're going to use Euler's formula again. So we know this is going to be S. And with S, that's going to be JW, as we know. And when it comes to the Euler's formula, it's always going to be that cosine. I keep going. So it's going to be this plus the sine was negative. So because of that negative, it's going to be negative minus sine of the W. So now, when it comes to the amplitude square, it's always going to be that I squared plus R squared, which is equals to cosine sine squared plus cosine squared. And that is equals to 1, as we know in trig functions. So for this, the tangent is going to be sine 0 divided by cosine. It's basically, that's how the tangent works. The tan of that is the sine. So when we're finding for like the phase lag itself with the W, that's what gives it like those disruptions. That's what makes it unstable. So it gives it that time delay rating. So I was going to do tan inverse of tan. So basically they will cancel out. And this will give us what was I releasing there? I was in the wrong hole. So that's just to create like disparity. So that it won't look like we're using the same sign, meaning like they are not the same, they are different angles. So it will just show what are different. So that'll be minus, sorry. So that'll be minus now. So that'll give us what the phase lag will be in that case. Okay. So now what part is next? So show and explain how a first order system with time delay may become unstable with proportional only control, PO control. That's what we call that. So now let me stop there. Let me set things up. Now I'm going to computationally show how the first order with the time delay, that time delay that we just like show the with the W. That's what we're going to show how that inclusion kind of like shows like the time delay in the whole function and all that down the line. So let me run. Here's recording. So now everything has run. So now we can start advancing to the next. And I feel like all this is kind of connected as well because we're going to include W. But now we're going to switch things up a bit. So we know W P dot length space minus 2. We choose 1.5 this time because last time we went with, I think last time we went with last time we went with 2. Yeah, last time we went with 2. So this time we're going to go with about 1.5. So we'll pick length space 1,000. So everything pretty much will be like the same thing, but like is there going to be that what's it called? It's going to be that time delay that shows the difference in how the graphs will look. So now let's get to that. So what are these KC and K do we have for what do we even pick? Let me check my notes. Let me check what values we picked last time. Let me check that real quick. So now these are the values that they give us to use in terms of like KC2, K1, and tau 10 in this case. Should I rename them? How should I rename them? I think I'll leave it the same way. Um, so basically, we'll do what we did here, how we got the RI value. So now I'm going to do that again. But like I said, we're looking for that delay, that time delay is what we're going to use. Sorry, I did not. So let me check the formula for that. Okay. So that's the usual, is that usual KC multiplied by K? But it has the usual, the tau, S, and J, but now there's a bit of a twist to it. So it's multiplied by E, the natural log, E, the exponential rate. That's what I mean. So minus 0.1 multiplied by W, as we know, multiplied by the J, which you know. Why is it just pressing the wrong thing? 1J. Then that whole thing will now be, because we have no brackets. So yeah, that will divided by what we normally use, the tau, I'll put a bracket around that. So I think it was the same thing. Let me just remove this, because when I'm looking back then, we're looking at 3 tanks, but here it's just going to be like this. And it's gonna get ready, bro. This. So yeah, I think it needs, what did we pull last time? Yeah, so we pulled this as well. This is key. We're showing what the R is. The R is the real image, the real, and the other one is the image. We'll put that in. I think I should. Let me just rename it so that it won't get. Let me just avoid errors. R1, 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 R1. Yeah, R1. Same thing to turn this from. This is just to turn this from radians to degrees, like we did before. Then AR1, the amplitude ratio is just the absolute value of the RI reading. Okay, let me see if that runs. That runs. So now it's just I'll just copy these that we did here. Just to change the figure name. And I also adjust these values as well to show. So we have YW1, W1 is 1. One day I'll learn. Yeah. Right now, I'm just changing manually. Still trying to figure it out. I'll check Google one day. Okay. Seems like everything's good. Is it not picking up anything? Yeah. Oh, what is? Oh, that. Let me see which one was which. KC1. This is meant to be K1. Still nothing. Oh, forgot to change these values. Okay, so we have for the the amplitude ratio. Now we need to get the phase. What's wrong with the phase? Let's see what's wrong with the phase. All right, one. And like that, we have our graphs. So we can see when we attach that time disturbance, we can see what the difference in the shapes of the graphs will look like. So it just really shows how that time delay makes it unstable with only the proportional control. So I mean this is okay, but like the phase, you can see the phase is what's going to be affected the most, really. Look at the compare, you can compare both. You can see the difference in values. Let me extend. So kind of see what the difference is between these two. Let me extend these as well. So right below as well. But gap, this one is like already like already 100 past 200, but this one is just 100. So like you can see the disparities on the time delay causes really. So yeah, I feel like that's all for part A. And yeah. I'll see you in part B. Thank you.